Hi Aaron and Jonathan. This is really sad that there's only 3 of the 5 of us and that we can't get together anymore. So I have this nightmare that we'll never be all together again. But it's just a nightmare. So please come back and make sure my bad dream does not come true. Alright, today we're talking about looking at a series. Here's a simple one where R happens to be, we did the nth term test for divergence by taking the limit of the nth term. It went to 0, so that particular test fails at that point. We don't know if it converges or diverges, but we did recognize this was geometric with R equals 1/2. So that means we could throw it into this formula and adjust for the fact that it didn't start at 0. We had to back out that value where n equals 0, where we took out a 1 from the 2 generated by the formula, and we got it converging to 1. I'm going to show you a picture now, and this I would like you to write down, if you haven't started already. Write down this series, and let me show you it with a picture. So, 1 I'm going to represent as a one big square. So, we can think of it as an area. So say we have a 1 by 1 square. So the area of that is 1. So this problem starts out with 1/2. So I'm not really counting this, I'm counting 1/2. So I'm going to color in 1/2. So to that I'm going to add 1/4. So I'm going to take 1/4 by taking this side and dividing it in half. So now I've got pictured 1/2 plus 1/4. Next, 1/8. So there's 1/8. So I'm down to here. 1/16. And I'm going to go even further than I actually wrote out. 1/32 would be half of this. And then 1/64th and 1/128th, and on and on and on and on. And now my chalk has got too cumbersome to show you the rest.
Should this be a new section, or is this still in the nth term test?
It is sort of in between, so you can leave it on the tail end of that section, and because when we start the next discussion, I will title it something else. So notice, does this convince you that this goes to 1? You can see that I'm going to keep shading in smaller and smaller parts that will get closer and closer to filling in this whole 1 by 1 square. So, which is representing 1 as the answer. So I thought that was cool, and I'd share that with you. Alright, before we leave this topic altogether, I always have a little bit of a loose end or two. So, let's see, sometimes I am tempted, and I'm afraid you might find yourself tempted as well, to forget the fact that this 0 infers that it does not, we don't know if it converges or doesn't. Here's where I'm sorely tempted, and I hope you aren't, but I am, to say it converges. So look at this one and write it down. Again, we're sort of ending up yesterday's discussion, so you can write it in that area. I want to look at this progression. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So we go on out, and it's obvious that the nth term is 1 over n, and then it goes on from there infinitely. So looky here. 1 plus 1/2 plus 1/3 and so on. If I take the limit of the nth term, which is 1 over n, what happens, Morgan, when I take the limit as n goes to infinity?
0.
Right. When you take 1 pi and divide it by a very, very large number, say 1,000, you don't get much of the pi. But if you divide it by the infinite number, you get 0. So 1 over infinity is 0. So we've met that time and again. So I have this gut feeling that this converges. So I'm tempted to use the nth term test and say, well, these terms are getting smaller and smaller, so it's got to converge to something. But actually, this one does not. It's very interesting that it doesn't. You wouldn't think it was a whole lot different from this, because it's getting smaller and smaller and smaller. If I try to draw it, maybe that will convince you that this does not converge. I'll try with this, but I'm going to fail, so I'll just warn you. In fact, you might try not to draw this unless you find the drawing helpful, because it's going to be a failed drawing. See, this one starts with 1, so I have to start with the big block. Then it adds a half, so I gotta have to eyeball half of that block. So 1 1/2. Then I gotta eyeball a third. I don't know what a third looks like. Maybe that, like a third of this. And then a fourth. I told you this would be a failed drawing. Then a fourth. And then a fifth. I don't know. I guess they would all be the same length, wouldn't they? I told you it would be failed. But 1 plus a half plus a third plus a fourth plus a fifth, it doesn't seem to be, at least it's not approaching 1. But could it be approaching 2 or some other number? Actually, this will continually grow. It's going to grow slower and slower, and eventually grow slow, but eventually it will just keep on going and not converge to any number. So this is, like I said, a failed drawing. Let me show you one that might convince you. You tell me if it does or doesn't. This is one you can write down. Anybody timing this?
No.
Okay, what do you think we've done?
3 minutes, 50
Nah,
seconds.
longer than that.
Like 4 or 5.
All right.
No.
Do you have anything?
Yeah.
Like 5 minutes for me, and then we'll shut that one down. All right. I'm going to give you a drawing. Let me get rid of everything else except what we're talking about. Goodness. Hilarity reigns. All right. So, this drawing, I'm going to draw like this, and I'm going to draw an old friend of ours. See if you can draw it. Y equals 1 over x. And I'm only interested in that graph in the first quadrant. So if you would draw an old friend of ours, the reciprocal function, from our pre-calculus days. Did you recall that in the first quadrant it looks like this? If you plugged in a few numbers like 1, 2, and 3, you would see, and if you put in 1/2 and 1/3, you would see this curve would be correct. So I'm going to start here at 1. That's what I'm interested in, the 1. And I'm going to build a box. The box is going to go, and its width is going to go from 1 to 2. And it's the top of it is going to correspond to that point on the graph. So can anyone tell me what the area is? If that is the height of this box, remember that point is when we put 1 into that function. So what's the height times the width here? Brendan, can you visualize what I'm trying to get you to say?
Well, the width's 1.
Right. And so what's the height? If this is the x value, it's on the function y equals 1 over x. So the height is the y part. So when I put 1 into this, what do I get?
1.
Right. So my x and y axes don't have the same scale, but that's okay. So this is 1 and that's 1. So the area is 1 there. All right. Now I'm going to build the next box by going from 2 to 3. So, Gianni, what is the area in this box here? I need height times width. The width is easy, it's
The
1.
width is 1, the height is 1/2.
It is. Notice when we put 2 into this formula, we can get the y value, which is the height of this box. It's 1/2. Morgan, you're up to bat. The next box is between 3 and 4.
1/3.
Right, and so on. Isn't this cool? I'm generating a picture of this function. And I'll just go up to like 1/5. 1, 2, 3, 4, 5. 6 divisions will take us up to 1/5, or 6 numbers. All right, so if I could convince you that part of that diverged, then perhaps I can convince you that this series does. So I'm going to need a color. I know orange and yellow don't show up much different on the video. Let me try this green. All right, so if I only look at this part, the part under the curve, I can do that with what tool? What calculus tool can I use, Brendan?
Derivative.
Nope, that's the slope, the other one.
Integral.
Right, the integral is the area under the curve, so this would go from 1 to 6. 1 to 6 of this function, 1 over x dx. So there, this will only take, I'll be only showing you the part that is colored or striped there in green. So when I do that from 1 to 6, let's go ahead and take that integral. So Johnny, what is the integral of 1 over x?
1 over x squared minus 1 over x squared.
Minus 1, this one is like x to the minus 1. He has a special case.
Oh, integral. I
Yeah,
was thinking
yeah,
derivative.
you were.
ln x.
All right, ln of x. So, and we're going from 1 to 6.
I'll blame Brendan. for
Oh,
that
you
one.
know what? I'm not stopping at 6. I'm sorry. This is an infinite series. So, I'm going to go to infinity. So, what's that called, Morgan, when we have one of the limits of integration is infinite? Remember what we called that?
No.
An improper integral.
Oh,
So we did that by bringing out the b or the t or some other value. The integral is
Oh,
the
yeah, I
limit
know
as b
this.
approaches infinity of 1 to b, 1 over x dx. So now we still need Gianni's answer, the ln, except that we still have this limit in front of it as b goes to infinity of ln of x evaluated from b to 1. So let me step back and you'll recall how we did that improper integral. So, Brendan, when you're putting in this b, this is supposed to be b, it almost looks like a 6. So when you're putting the b, we get the ln of infinity, or the ln of b, the limit as that goes to infinity. So Brendan, help us with the ln of b.
Infinity.
It is, because the graph, this will be our little collection of graphs today. The graph of ln goes like that. And it's getting infinitely larger. So this whole thing diverged. So this is diverging, it's not approaching any value, it's getting larger and larger. And that's only the part that I've striped. This series is even bigger. So can you see if this part diverges, must not also the larger series that we have represented here in the yellow blocks? Yes?
It's been 5 minutes.
Okay. See this part